Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. As promised in a previous video on linear relations, this video provides algebraic proofs for both the parallel lines theorem and the perpendicular lines theorem. Now, what normally happens in a typical high school setting is that teachers will provide the students with these theorems, that is to say the parallel lines theorem and the perpendicular lines theorem, but usually these are presented without proof. And if they provide any sort of proofs whatsoever, they're usually geometric proofs or some sort of a similar triangles type proof. And in this video we're going to attempt a purely algebraic proof for both theorems. For both the parallel lines theorem, we're going to use a proof by contradiction approach, and for the perpendicular lines theorem we're going to use a direct approach using primarily the Pythagorean theorem. So without further ado, let's turn to slide 1. Part A, parallel lines proof. Let's see what we're given. We're given that M1 is the slope of L1 and M2 is the slope of L2. And we're also told that two lines, L1 and L2, are distinct. In other words, the two lines are not coincident. This is a very important fact that we're given at the outset, that the lines must be distinct. In other words, the lines do not lie on top of each other. Because if the lines do lie on top of each other, there's no point in doing the proof. The lines are identical and therefore they must have the same slope. They're exactly the same line. So there's no point in embarking on that sort of proof if the lines are indeed coincident. So it's very important that you understand that the two lines must be distinct. Okay, so the whole proof hinges on this. So let's see what we need to prove. It says L1 parallel to L2 if and only if M1 is equal to M2. Now the symbol for if and only if is the equivalence symbol. It's also known as a double implication symbol, and it's also known as a bidirectional symbol. This is an equivalence statement. It's saying prove that the left side is indeed equivalent to the right side. Now, what does that mean exactly? That means we have to proceed in both directions. Okay, we have to proceed in the forward direction, and then we have to restart and proceed in the backwards direction. In other words, we're first going to have to prove that if two lines are parallel, then their slopes are equal. And then, if two slopes are equal, the lines must be parallel. So it's going to be a bidirectional proof. So without further ado, we'll embark on the proof in the forward direction. Here's part 1. What do we have to prove exactly? L1 parallel to L2 implies that M1 is equal to M2. That is in the forward direction. In other words, we're given that two lines are parallel. We must prove that the slopes are equal. And again, this is going to be a proof by contradiction. And proofs by contradiction are somewhat confusing. A lot of students get confused and teachers get confused as well. So you've got to go through it very, very carefully. It's a bit of a mind bender, these proofs by contradiction. Okay, I'll try to ease the pain. Essentially, what we're going to do is assume that the right-hand side is false. Based on that assumption, we're going to show that something else that was already given is being contradicted. In other words, we're either going to contradict that the lines are parallel or that the lines are distinct. Because at the outset, we said that the lines have to be distinct. So we're going to assume that the right-hand side is false and then come up with some sort of way of showing that that contradicts what's already been given. Okay, so let's embark on the proof. Since L1 is parallel to L2, of course, that's what's given. Okay, there are no ifs, ands, or buts about what's given. Then by definition, the lines cannot intersect. That's by definition of parallel. So now we already know the lines cannot intersect. We continue with a proof by contradiction. And by the way, the symbol for contradiction is a right arrow and a left arrow, and they're colliding in the middle. So that's the contradiction symbol. Now, the assumption. We assume that the right-hand side is false. Another way of saying that is to assume that M1 is not equal to M2 is true. Okay? So one way of saying that the right-hand side is false is by saying that M1 not equal to M2 is in fact true. That's the assumption. Okay? The assumption is not necessarily true. It's just something that we're assuming for the time being. Now, based on that assumption, we embark to show that the assumption is indeed false. Now, let's say the assumption were true, that we have two lines with unequal slopes. Then for certain we can search for a point of intersection. So that's the next step. We search for the point of intersection, POI, of L1 and L2. Now, before we search for the point of intersection, we need to define L1. Now, L1 is defined as y equals m1x plus d1. Of course, you recognize that as a slope-intercept form for L1. m1 is the slope, d1 is the y-intercept. Likewise, L2 is defined by y equals m2 dot x plus d2. Again, this is a slope-intercept form for L2. M2 is the slope, and D2 is the y-intercept. Now, to find the POI of two lines, we set y equal to y. This is like the method of substitution. When we set y equal to y, of course, the right-hand sides must be equal. So we set the right-hand side of L1 equal to the right-hand side of L2. Now we solve for x. We can use a little bit of backward bin gathering to solve for x over here. We can open up an x bin on the left. Over here we pick up an m1, drop it inside the bin. On the right we have m2 dot x. So we pick up an m2, bring it over, becomes minus m2. Close up the bin. Then we hit the equal sign. On the right hand side we open up a constant bin. We drop in d2, and then d1 becomes minus d1 when you bring it over. And this is the all-important equation that we'll be dealing with in the next slide. So if you can take like a mental photograph of that equation, I'm going to go over to the next slide. There are two possible cases that arise from that equation. One case is where the coefficient of x is equal to 0. When that happens, division by 0 is not allowed, so you cannot solve for x. Okay? But of course, when m1 minus m2 is equal to 0, that means the left-hand side is 0. And if the left-hand side is 0, then the right-hand side must be 0. And if the right-hand side is 0, then d1 must be equal to d2. And again, if m1 minus m2 equals 0, then it must be true that M1 is equal to M2. So if we stand back a little bit, this says that the slopes of the two lines are equal and the y-intercepts are also equal. But if that's the case, then they have exactly the same equations. In other words, their SIF, slope-intercept forms, are identical. If that happens, the two lines must be coincident. In other words, they have to be identical. But if they're identical, that contradicts the fact that the lines are distinct. We said that the lines were distinct at the outset. Okay, that's what we said in the very beginning. Now all of a sudden, that assumption that we made on the previous slide led us to this contradiction, that the lines are coincident. The lines cannot be coincident and distinct at the same time, and hence the contradiction. Now the second case is where the coefficient of x is not equal to 0. Okay, let's go back to that equation. This coefficient over here is not equal to 0. So let's say this coefficient over here were like the number 3. Then you can divide both sides by 3, perfectly legitimate. Whereas in case 1, we had a 0 over here. You're not allowed to divide both sides by 0. But in the case that you have a 3 over here, you can certainly divide both sides by 3. And you can get a legitimate x-coordinate for the POI, which is essentially what we did over here. Okay, we solved for the x-coordinate of the POI by dividing top and bottom, by dividing both left and right-hand sides by M1 minus M2. So here's the POI. Let's go back to the previous slide. When you solve this for x by dividing both sides by M1 minus M2, you get this POI. And of course, this POI exists because M1 minus M2 is not equal to 0. It could be like a number like 3. So you have D2 minus D1 all over 3, which is perfectly legitimate. And here we have the POI. The POI is in our hands. But that contradicts the fact that the lines do not intersect. If we have the POI at hand, doesn't that contradict the fact that the lines do not intersect? Don't forget, the lines have to be parallel. The lines are parallel. And over here, we're saying that the lines intersect. There's the POI right there. There's the x-coordinate of the POI. So on that one hand, we're saying that the x-coordinate of the POI exists. There it is. On the other hand, we're saying that the lines are parallel. That is a contradiction. Okay, so we conclude that M1 not equal to M2, which was the assumption, is in fact false. So that M1 equal to M2 must be true. Okay, so we've shown that the right-hand side must be true. Okay, we were given that the lines were parallel, and we used proof by contradiction to show that the right-hand side is true, which says that if two lines are parallel, then their slopes must be equal. Now let's go in the backwards direction. In the backwards direction, everything has been flipped now. Now we're given that the two slopes are equal, and we have to show that the two lines are parallel. We're given that the slopes are equal, and we have to show that the two lines are parallel. This is the backward version of what we just finished doing. Okay, so we're given this, we have to prove this. Exactly the opposite of what we just finished doing. Now again, the assumption is going to be the opposite of the right-hand side. The opposite of the right-hand side is that L1 and L2 are non-parallel. Okay, so let's embark on the proof here. Again, we embark on a proof by contradiction, and there's the contradiction symbol. we start off by assuming that L1 is not parallel to L2 is a true statement. In other words, L1 not parallel to L2 is a true statement. The opposite of this is true. That's what we're assuming. This means that L1 and L2 must be distinct intersecting lines. Okay, if the lines are not parallel, thus they must be distinct because we said that at the outset, and they must be intersecting because non-parallel means intersecting, and hence a POI must exist, provided that this assumption, of course, is true. So based on this assumption being true, we know that the lines are distinct and intersecting, and therefore a POI must exist, a point of intersection must exist. And we can then proceed to find it as follows, just like we did in the previous proof. Again, L1 is described by y equals m1x plus d1, slope-intercept form for L1. L2 is described by y equals m2x plus d2, slope-intercept form for L2. And again, to find the POI, because that's what we're searching for, we set y equal to y, and there's y equal to y. And of course, this means that the right-hand side is equal to the right-hand side, and that's what we did. And again, to solve for x, we can use a little bit of backward bin gathering. We open up an x bin on the left, drop in an m1, m2 becomes minus m2. You hit the equal sign, open up a constant bin on the right, you drop in a d2, and then d1 becomes minus d1, and voila, this is the key equation that we have to deal with. Again, there are two cases. The first case is that the coefficient over here is 0, and the second case is that it's not equal to 0. So let's have a look. Again, there are two possible cases, just as in the first proof. One case is where that coefficient is equal to 0. Then division by 0 is not allowed, and we get a 0 on the left-hand side. And of course, if the left-hand side is equal to the right-hand side, that means the right-hand side must be 0 as well. Okay, we conclude that m1 is equal to m2, and d1 is equal to d2, just like before. Of course, this says that the lines are coincident. Their slopes are equal, their intercepts are equal, and the slopes must coincide. The lines must coincide. In other words, they're identical. Now, does that contradict anything? Okay? If the lines coincide and they're identical, they cannot be distinct. And of course, we said that they have to be distinct at the very outset. Okay? So the assumption eventually led to this contradiction. Based on the assumption, we conclude that the lines are coincident. But this contradicts the fact that they're in fact distinct. Okay? They were distinct because we made them distinct at the outset. Now, case 2, that's where the coefficient is equal to 0. Now, when the coefficient is not equal to 0, then we're not dividing by 0. And we can actually solve this equation for x by dividing both sides by m1 minus m2. And that's what I did over here. Okay, so if m1 minus m2 is not equal to 0, for example, m1 minus m2 is equal to 3, then division by 3 is certainly allowed, and we get the x-coordinate of the POI as x equals d2 minus d1 all over m1 minus m2. And of course, m1 minus m2 is something like 3, so this division is certainly allowed, and voila, we have the x-coordinate of the POI. So now we've identified the x-coordinate of the POI. Does that contradict anything? This contradicts the fact that we found the x-coordinate of the POI, contradicts the fact that m1 is equal to m2. Okay, you recall in the beginning that m1 was equal to m2. That was gospel truth. That was what was given. So we've just contradicted what was given. Because on the one hand, we're saying m1 minus m2 is not equal to 0. And then what's given at the outset was that m1 is equal to m2. These are contradictory statements. Okay? So what do we conclude? We conclude that the assumption is false. So that L1 is parallel to L2 is true. Remember, the assumption said that the lines were not parallel. Okay, so if the assumption is false, then the opposite of the assumption must be true. So that L1 is parallel to L2 is indeed true. Now, we've gone in the forward direction, we've gone in the backwards direction, and this completes the bidirectional proof that L1 parallel to L2 if and only if M1 is equal to M2. In other words, if two lines are parallel, then their slopes are equal, and if two slopes are equal, then the lines are parallel. And that completes the bidirectional proof. If you got a massive headache from that parallel lines proof, I don't blame you one iota. Okay, for one, it was a bidirectional proof, so we had to do it twice. And for two, it was a proof by contradiction, which is normally quite confusing, and it's hard for people to wrap their heads around. And you normally have to go through proof by contradiction type proofs a number of times in order to make any sense out of it. So if I give you a massive headache, I'm sorry about that, but sometimes that's what happens in math. I myself try to avoid proof by contradiction whenever possible, but sometimes it's impossible to avoid. So I have to bite the bullet, and it becomes unnecessary evil. So there's nothing much we can do about it. So anyway, sorry for the headache. And now we're going to talk about the perpendicular lines proof. And I'm going to give you a different kind of headache this time. I'm going to give you an algebraic headache. Okay, so essentially we're going to use the Pythagorean Theorem primarily for this perpendicular lines proof. And before we get going with the proof, I just want to discuss some items on this page in front of you. Essentially, I set up an x-axis, a y-axis. I declared this point to be the origin. I drew a line, called it L1, and I drew another line, and I called it L2. And I declared L1 to have equation y equals m1x plus d1. Of course, you recognize that is slope-intercept form. I also called this line 2 with equation y equals m2x plus d2. Again, slope-intercept form. And then after I did that, I declared the point of intersection over here to be A with coordinates a1, a2. Then I went a certain distance along L1, and I stopped, and I called that point B with coordinates b1, b2. And again, I started off at A, and I went a certain distance along L2, and then I stopped, and I called this point C with coordinates c1, c2. And one more little note here. You'll notice that I indicated that B2 is equal to M1 bracket B1 minus A1 plus A2. That'll be clear during the proof. And then I also said that C2 is equal to M2 bracket C1 minus A1 plus A2. And again, that will be made clear during the proof. But essentially, this equation here comes from the equation for L1 and the fact that both B and A lie on L1. And similarly, this equation here comes from the equation for L2 and the fact that both A and C lie on L2. Okay, so I think that's enough for that diagram there. Just try to take a mental picture of it as we go through the proof. So part B, perpendicular lines proof. we're given M1 is the slope of L1 as usual. M2 is the slope of L2 as usual. And we're also told that line 1 and line 2 are distinct, aka not coincident. And we're asked to prove that L1 perpendicular to L2 if and only if M1 dot M2 is equal to -1. The if and only if tells us that we have a bidirectional proof again, just like we did for the parallel lines proof. And of course, this is called the equivalent symbol or the double implication symbol. So this is an equivalent statement. Okay, the proposition on the left is equivalent to the proposition on the right. Okay, so it's asking us in words to prove that that perpendicular lines and the product of the slopes is equal to -1 are essentially equivalent propositions. So they're interchangeable. So we're going to go through a forward proof first and then a backward proof to finish it off. So a forward proof and then a backward proof. So let's go on to the next slide. Part 1 will be the forward proof. L1 perpendicular to L2 implies that M1 dot M2 is equal to -1. So we're given that two lines are perpendicular, and we're asked to prove that the product of these slopes must be equal to -1. So if this is true, we must prove that this is true. So proof. Since L1 is perpendicular to L2, then the two lines must intersect at some point. Let's call that point A with coordinates A1, A2. Next, we choose B with coordinates B1, B2, and we assume that it's not equal to A, and that will be a point on L1. And then we choose C with coordinates C1, C2. That will also not be equal to A, and that will be a point on L2. So B is on L1 and C is on L2, as we indicated in the diagram at the start. Now, since L1 is perpendicular to L2, that was given, then triangle BAC is a right triangle with angle BAC equal to 90 degrees. Okay, why is that true? Because L1 perpendicular to L2 means that AB and AC are perpendicular, and therefore triangle BAC forms a right angle triangle, and of course that implies that angle BAC is 90 degrees. So that means that we can use the Pythagorean theorem. So the Pythagorean theorem, PT, for triangle BAC then reads as follows. Okay, AB squared plus AC squared must be equal to BC squared. Standard Pythagorean theorem. Okay, so this statement is for certain because we're already given that the two lines are perpendicular. So this is not something we have to prove. This is something essentially that we're given, and it follows from the Pythagorean theorem. So using the distance formula, AB squared becomes B1 minus A1 squared plus B2 minus A2 squared. That will account for AB squared. And then similarly, AC squared is given by bracket C1 minus A1 all squared plus C2 minus A2 all squared. Okay, so no problem there. And similarly, BC squared will be C1 minus B1 all squared plus C2 minus B2 all squared. Okay, so this is just a statement of the Pythagorean theorem. We'll call that equation 1, and we're going to hold equation 1 for further processing. So I want you to pay attention to the right-hand side of equation 1 because that's the part that we're going to be dealing with. So there's the right-hand side of equation 1 right there. And now we're going to pull a really, really fast trick, and it's called the add-subtract trick. You see the C1 minus B1. It's identical to C1 minus B1 here, except I subtracted a1 and added a1. So I've done nothing. Okay, let's go through it again. You see the c1 minus b1. There's c1 minus b1. I subtracted a1 and added a1. That's all I did. Now I do the same thing for the second term. c2 minus b2. There it is, c2 minus b2. I subtracted a2 and added a2. So effectively, I have done nothing. All I did was form two groups. I formed two groups. And now I'm going to expand using perfect squares, because this is a perfect square and this is a perfect square. So when we expand, look to see what we get. We get c1 minus a1 all squared. There it is. We get a1 minus b1 all squared. There it is. And then we get the cross term. The cross term is two brackets, c1 minus a1, bracket a1 minus b1. And I put it down here. We'll do the same thing over here. When we expand mentally, we get c2 minus a2 all squared. I put it down here. We get a2 minus b2 all squared. I put it down here. And then we get the cross term. We get a two brackets, c2 minus a2, open bracket, a2 minus b2, and then I put it down here. Okay? So the key over here was this add subtract trick, the add subtract trick. Okay, so now we're at this stage right here. We have equation 2, and what we're going to do is replace the right-hand side of equation 1 by equation 2. We're going to replace the right-hand side of equation 1 by equation 2. Okay, so now when we do that, and I did it sort of mentally because otherwise I would have taken up a whole page to do. Okay, this over here really belongs on the right-hand side of equation 2 now. Look at the terms. The first four terms here, they're exactly the same as the first four terms on the left-hand side. Actually, there are only four terms on the left-hand side, but these four terms here on the left-hand side of the equal sign are identical to the first four terms here. So these four terms cancel out with these four terms. And what we're left with is just 0 on the left-hand side because of all the cancellations. And we're left with this on the right-hand side. This is on the right-hand side. Now we divide everything by 2. Okay, so we divide both sides by 2 to get rid of those 2's because we don't really need them. And then what I did was I took this guy and I moved it over to the left-hand side. Okay, and I read the equation backwards. When you do that, this is this, and then this gets transferred over to the left, and it becomes this. Notice the minus sign over here comes about from the transfer. When I transpose this over to the other side, I get a minus sign appearing out front. So now the next step, when we look at this product, I'm going to divide both sides by this product. There we go, right there. Divide by that product. When you divide the left-hand side by that product, use a big division bar. In the numerator, just copy-paste. There you go. In the denominator, copy-paste that. There you go. On the right-hand side, okay, this has been canceled, and we're left with a -1. Now, finally, what we're going to do is split this and rewrite it the other way around. All I did was flip these. I didn't have to, but I just thought I would flip them, make it look more cute. So anyway, all I did was grab this, rewrite it here, grab this, rewrite it here, grab the minus sign, rewrite it there. Okay? Now, if you look at this carefully over here, this is just the slope of AB. You can verify this is just the slope of AB. And this is just the slope of AC. But if AB lies on L1, then the slope of AB must be M1. And if AC lies on L2, then the slope of AC must be equal to M2. So that means this ratio can be replaced by M1, and this ratio can be replaced by m2. So finally, we get that m1 dot m2 is equal to -1. And voila, that's exactly what we needed. If we go back to the start, okay, we started off with this, which enabled us to invoke the Pythagorean theorem for triangle BAC, and then we wound up proving that m1 dot m2 is in fact equal to -1. So the forward proof is over as required. In the next slide, we'll start up the backwards proof. So this is part 2. Prove m1 dot m2 is equal to -1. That implies that L1 perpendicular to L2. In other words, if the product of the slopes is equal to -1, we have to prove that the lines are perpendicular. Okay, so we'll start up the proof. Let A with coordinates A1, A2 be the point of intersection of the two lines, so that we can write these equations down. Y is equal to m1 bracket x minus a1 plus a2. Well, you recognize this as the point slope form of L1. M1 is the slope, and A1 comma A2 is the point, which of course are just the coordinates of capital A. Likewise, L2 can be written as y equals m2 open bracket x minus a1 plus a2. For the same reason, m2 is the slope of L2, and point A with coordinates a1, a2 is a point on L2 as well. So A is a point on L1, and A is also a point on L2, and these are both point slope forms. Okay, next, introduce a point B with coordinates b1, b2, not equal to A. You don't want B to be the same as A, and let that be a point on L1. And also introduce the point C with coordinates C1, C2, also not equal to A, and let C be a point on L2. Just as in the diagram that we had to start off with. We'll briefly go back. Okay, there's the point B on L1. There's the point C on L2. A is just the POI between the two lines. And let's go back. Okay, now, since the point B lies on line 1, there's the point B right there. There's line 1 right there. We can replace the y value by b1 and the x value by, the y value by b2 and the x value by b1. When you do that, you get b1 is equal to m1 bracket b1 minus a1 plus a2. Okay, likewise, since the point C lies on L2, we replace the y by C2 and the x by C1. To get the equation, C2 equals m2 bracket C1 minus a1 plus a2. Okay, so this equation is true because both A and B are on line 1, and this equation is true because both C and A lie on L2. So we have to keep these two things in mind. Okay, so we'll go on to the next slide. We now show that triangle BAC satisfies the Pythagorean theorem. So that's the mission from here on in, is to show that triangle BAC satisfies the Pythagorean theorem. And we start off by saying AB squared plus AC squared. Again, distance formula. Okay, those two terms are AB squared. Those two terms are AC squared. That should be no problem by now. Now the key right now is to replace the B2 and the C2 over here. What are they going to be replaced by? What we came up with down here. So B2 gets replaced by the right-hand side, and C2 gets replaced by the right-hand side. Okay, so making those two replacements, This is just a drop down. Then we make the replacement for B2. There it is right there. This is just a drop down. Make the replacement for C2. There it is. And we've got everything. Now you'll notice A2 minus A2, they just cancel. A2 minus A2, they just cancel. So we continue. We drop this term down here. We drop this term down here. Then over here, the A2s are gone, and we get M1 squared. There it is there. And we get B1 minus A1 squared. There it is there. And we get M2 squared. There it is there. And finally, we get C1 minus A1 all squared. There it is right there. Okay? So now, all together, how does it read? It reads AB squared plus AC squared is equal to this little bit of a mess over here, which I call equation 3. And now we're going to hold equation 3 for further processing. What we're going to be doing is replacing this. Okay, we're going to be replacing these two terms. These two terms go along for the ride. Okay, so let's go on to the next two slides. Now, you'll recall that we have expressions for C2 and B2. Okay, let's go back so you recall what those expressions are. There's the expression for B2. There's the expression for C2. Now I'm going to go back. And so now that we have both those expressions, we can certainly use them in the next step. There's a replacement there, and then minus, there's a replacement there. You'll notice that the A2s cancel. Okay. And we're left with M2 bracket C1 minus A1, and then minus M1 bracket B1 minus A1. And that's all squared. So again, we have a perfect square, and we're going to expand. Okay, to start off with, we get M2 squared. There it is right there. We get C1 minus A1 squared. There it is. Then we expand this. We get M1 squared. There it is. B1 minus A1 squared, there it is. And finally, we get the cross term. The cross term is minus 2, M1, M2, bracket C1 minus A1, bracket B1 minus A1, and there it is right there. Okay? So these are the two perfect squares, and there's the cross term. Now, this is on the left-hand side. These two are on the right-hand side. The next move is to bring this term over the left-hand side so that we have an expression for this. So if we do that, that says that this, which is that, is equal to C2 minus B2 all squared plus 2 M1 M2 bracket C1 minus A2 B1 minus A2. There it is right there. Okay, because when we move this over, it becomes a plus 2. Okay, so I hope you're still with me here. And now we're going to replace the right-hand side of 3. Let's look to see what the right-hand side of 3 is. There it is right there. Take a picture of it, the right-hand side of 3. And of course, that is the right-hand side of 3. We're going to replace that by this little bit of a mess. Okay? When we do that, let's see how it reads now. Okay, do you remember this guy over here? We replaced it, but these two get dropped down. Okay, so we summarize by saying AB squared plus AC squared. These are the two drop downs, and that replacement appears right there. Okay, so that replacement appears right there. The first two terms were already in the right-hand side of 3. You see the first two terms there? They're already there. So let's go back. So altogether we have this, and now what's M1 dot M2? Do we know what that's equal to? Maybe. Oh, it was given. It was given to be m1 dot m2 is equal to -1. That was given at the outset. Okay. That means that we can certainly replace the product m1 dot m2 with -1. And that is the key. Okay, that is the key. So now in the next line, that's what I did. What I did was I moved this term down here. I moved this term down here. And when you replace this product by -1, I moved this term down here. And then this term is over here. Now, if you look at this very carefully, you'll notice that this is a perfect square. Here it is down here. You get b1 minus a1 in brackets minus c1 minus a1 in brackets all squared. Let's test it out. When you square this, you get b1 minus a1 all squared. There it is. And then you get c1 minus a1 all squared. There it is. And then you get the cross term. There it is right there. So in fact, this is equal to this perfect square. Now you'll notice that we have a minus a1 here and we have a plus a1 there. So the a1s cancel and we're left with a b1 minus c1. There you go, b1 minus c1. So, all squared, of course. So this mess over here can be replaced by b1 minus c1 squared. So that's what I do in the next line. I replace it with b1 minus c1 all squared. And then, of course, the c2 minus b2 squared was already there. There it is right there. It was waiting. Now, if you look at this carefully over here, this is just an application of the distance formula for bc squared. Okay, bc squared. Just have a look at it. Distance formula for bc squared. So what do we get at the end of all this? We get that ab squared plus ac squared is equal to bc squared. There it is right there. That implies the triangle BAC satisfies the Pythagorean theorem. And of course, any triangle that satisfies the Pythagorean theorem is a right-angled triangle. And in this case, the right angle is angle BAC, so it's 90 degrees. We conclude that AB is perpendicular to AC, and that automatically implies that L1 is perpendicular to L2. Recall that AB lies on L1 and AC lies on L2. Therefore, the two lines have to be perpendicular. I think that's what we needed to prove. Yes, this is what we were given, and we needed to prove this, and voila, we came up with the proof as required. So this completes the bidirectional proof that L1 perpendicular to L2, if and only if m1 dot m2 is equal to -1. In words, if two lines are perpendicular, then the product of their slopes is -1. That's in the forward direction. And in the backward direction, if the product of their slopes is equal to -1, then it follows that the two lines are perpendicular. And that is the end of the perpendicular lines proof. And we've exhausted a lot of energy here. We've consumed a lot of energy in coming up with these proofs. I hope that you've been able to stay with me through these proofs, and I'm hoping that if there's something there that you didn't understand, you'll let me know about it, or you'll review the video a few times until you make sure that you really understand it. Okay, I have to grab some Tylenol right now, and I'm all wiped out. Thank you very much, and take care. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.